I'm going to have this slide up when I go up when I haven't started talking yet. Catherine de' Medici. She was the Queen of France for about 12 years. She was a Medici, and she was married to the king, but then it's not important. Her cousin was Pope Clement VII. He approved of the marriage of her and the king. And this story isn't making much sense. Okay, I'm going to have to fix this. This is the patriarch of the family. He started the Medici Bank, which used to be the most powerful and richest bank in Florence at the time, and all of Europe, actually. And the reason for it being so powerful and able to create a family that could basically take over lots of Europe, including queens of France, queens of England, popes, and lots of dukes and duchesses. And the reason it could do that is, partly a lot of luck, like right time, right place kinds of stuff, but also because they had a very powerful abstraction that other banks weren't using. That abstraction is called double entry bookkeeping. Double entry bookkeeping is standard accounting practice now, but back then it was totally new, totally revolutionary, and it gave them a significant advantage over the other banks at the time. Florence at that time, you think of banking nowadays and you think, oh, it's so boring, it's kind of a very well understood system. You become an accountant, and accounting is boring and just like systematic and organized and stuff. But back then, Florence and banking was like the capital of banking. It was like Silicon Valley is today. It was tons of experimentation, tons of money, and this system is what won out. So you could kind of think of the Medici Bank as like the Google of banking. So let's talk a little bit about. No, I don't want to do this. Okay. So double entry bookkeeping won out against all these other banks. And it's sort of like, well, because it had a better abstraction, it's sort of like Google beating Yahoo as a search engine. Yahoo was a very popular search engine, and it had a certain model of search. And Google came in with a different model of search that was better and took over the industry. Now, search and Google are synonymous. And we see this happening a lot. Software is kind of taking over businesses. It's taking over our lives. It's having more and more effect on the world. And where does that leave us as programmers? People who actually make the software. Where does that put us? Besides, having lots of flexibility in jobs that we work at, and the kinds of jobs, and like lots of career prospects and stuff. Where does that leave us, who are the ones who write this software? And the software is becoming more powerful. Where does that leave us? Right? To me, that's a really important question. I think that we are able, as programmers, as sort of, at the moment, it's kind of like an elite who are writing this software, because not everyone can program right now. we are able to create tremendous business value in business value, political value, whatever kind of value you want, but by creating these very important abstractions. And that's what I want to talk about today. Okay, wait a second. I'm going to skip because I need to revise my slides. My name is Eric Normand. I'm on a mission to create a process that helps people build better abstractions so that we can actually realize this value for humanity. Some of that value is simply, helping a business make more money, get better customers, that kind of thing. But some of the value is also a personal value of being able to program things that make our individual lives better, which one day I hope that will happen. Today I'm presenting the current iteration of that process. Let's take a moment to deconstruct double entry bookkeeping, and I'm going to have to back up now. I will edit these slides. Okay, so double entry bookkeeping, just real quick, this is like a programmer's view, so don't get mad, don't get upset that I'm taking 4 years of accounting school and putting into a few slides. This is just how I think of it as a programmer. So there's two parts to this abstraction, two concepts. There are accounts and transactions. Accounts have a list of debits and a list of credits, and transactions are sort of like a different view. It's like one debit and credit put together, and they have the same amount. So it says what account you should debit and what account you should credit. And then you take all these accounts together, that's a book or a ledger. That's what accountants call it. Now, why is double entry bookkeeping so powerful? A lot of people will say, well, it's because when you run this equation, it has some error detection, a little bit of error detection. Like if you forget to put in a debit and you put in the credit, but no debit, you can see that it doesn't balance, right? That they're not equal. And that's true. And I think there is some value in that. But I also think that there's a deeper value that we need to get down deep into. So one of these values is that you can actually express this with a simple equation. You can actually express a law about how the accounting system works and what it should look like at all times. So this is something that's supposed to be true for all time. So you start with an empty book, no accounts, that's 0 equals 0. And then as you add debits and credits, it should always stay equal. Here's another law, that you have assets, that's asset account, and liabilities accounts and capital accounts. They're all different types of accounts, but this relationship should hold at all times. It's nice. Here's a more mathematical or lambda calculus way of writing it. So I have another law that they don't talk about so much as far as I can tell, but it's something that should be true and is a powerful thing. If you add a transaction to a book, here I'm gonna write on here. So you add this transaction to a book here, and then you add the second transaction. It should be the same as adding the second transaction first and then adding the first one, right? So what that's saying is that for any two transactions, the order doesn't matter. Okay, that you can add them at any order. And you think about it, that's actually nice because you don't know when checks are going to come into the bank. You mail a check in, what order do two checks come in? You can't determine that. And so the fact that it still works, that the accounting system still works in that setting, is an important feature of the accounting system. And then the other thing is you can express that in math, which is really nice. Okay, so I want to go deeper though, because this is not, we're not really getting at anything new. A lot of accounting systems that you could imagine could have laws. They might have different laws, but they could have laws. So one thing that happens, online in discussions among programmers is we talk a lot about abstraction, but we don't talk about what it's actually abstracting. Things are abstract in relation to things that are concrete. And so let's talk about the concrete thing. Oh, and I put a little Tweety bird there, so if you want to tweet that, please feel free. So to do that, I ask myself this question. What does this abstraction represent in the physical world? Abstraction is just the world of ideas and thoughts. What does it represent in the physical world? I'll give you a moment to think about that. Does anyone have an idea of what this abstracts in the physical world? All right. So I'm going to do my best at saying what I see in this. When we're talking about banking and accounting and money, we're talking about in the physical world, like the most physical possible representation of money is gold, right? I mean, certainly in our culture, that's how we see it. Gold is money, gold is value. And then the accounts are like a safe or a vault, and you put your gold in there. And a transaction, which is the other part of the abstraction, is moving some gold from one safe to another safe. So you have a bunch of safes, and that's your bank, and then you start moving it around, and those are transactions. I think that kind of covers all of it. So the thing is, what makes this powerful when you see this is that it's not just an accounting system that like says, well, we're going to just keep track of how much gold is in each safe so we don't have to count it all the time. Sort of like a cache or an index. What it's doing is it's tracking the movement of gold. You're writing a transaction down, and you're able to get a history, which is actually lost. When you move gold from one safe to another, you've forgotten where that gold came from. But by writing it down, you've actually made it into something concrete and something you can make laws about. So this is where I think that the double entry bookkeeping has actually created the most value, is that it is recording something that is lost. You could always go into a vault and count how much gold is there. You just have to weigh it. But you can't remember, or you could, but it's hard to remember where the gold comes from. Like whose money is going where, right? So that's where, like, you could imagine a system that didn't do that. But this system does, and that's where it gets its power. So the concrete physical representation is super important to finding a powerful one, powerful abstraction. Okay, well, we've gone from abstract down to physical, okay? But really, when we're dealing with features and user stories and stuff like that, specs, we're kind of given the physical. A user wants to log in, a user wants to send money to somebody, and like they have a deadline. Like, so all of those things are represented as like physical stories, and we're supposed to turn it into software, which is abstract. So we need to be able to go from physical to abstract, and that's what this process does. Okay. So let's get into the process that I want to talk about. I've been given this advice a lot. I think I've probably given it, can't remember. But it's something that we talk about a lot, is that you shouldn't just start writing the code. You should go lie down in the hammock and think about it. But let's write this process down, because this is it's a decent start. It's not perfect, but let's write it. Let's start there. So here's the process. You take an assignment, you think about it, and then you implement it. So to me, like, when I hear this, the only thing I think of is like, well, that's indistinguishable from procrastination. If I was a manager or something, business person paying for this programmer, I'd say, like, you're just thinking, like, what are you doing, right? Procrastination. And in my own experience, like, that's what it is too. Yeah, I'm thinking about it, like, come on, produce something. So, given that bad process, which actually I should strike this from the talk. It doesn't really help. It's meant to be funny, but it doesn't really work. Okay, so what are my objectives with this process? I want to create a process that anyone can follow that consistently produces good abstractions. And I'll talk about what good abstraction means later. But I want it to be something that you can just sit down and start doing. And then there's this other thing is, we work on teams now, writing software. And it would be really nice if we could collaborate when we do this, like, really important work, the think about it work. It's hard, it's not just brainstorming, it's not just like talk. You have to have some concrete process that people can follow that allows for this collaboration, like, structurally, like it's part of the process. My process is inspired by Conal Elliott's denotational design, which I guess it's a process too. I said in the abstract that this was denotational design, that I'd be teaching denotational design, but I feel like at this point, it was definitely inspired by it, but at this point I've gone in a different direction, and I've interpreted it in my own way so much that I don't want to call it that anymore. So sorry to disappoint. It's largely inspired by it. You should watch his own talks about it, but this is not denotational design. Okay, here are the steps. This is what I've got. It works, and we'll go over the steps. So 3 steps, not bad, and they're kind of roughly, you can read the slides. They're roughly equivalent or like isomorphic to the kind of design process that we might be familiar with, where you do requirements gathering, and then you do a spec, and then you implement it. Which is not waterfall, by the way. Just want to say that. Okay, physical metaphor. This is the one where I get the most objections. Okay, whenever you say you can take something that's like considered to be creative and turn it into a process, there's going to be people who object. But this one, by far, has been the one where I've gotten the most dissension. I've given this talk at a local meetup, and the first thing that people say when I say, "Oh, you need to find a physical metaphor," is, "Well, my abstraction or my assignment, my software or whatever does not have a physical metaphor. It's impossible." So I don't have time to go into this, but I'll just say that all of our experience, everything we talk about, everything we think about, comes down to our experience in the physical world. And so if you don't have a physical metaphor, it's because you didn't even try. They raised their hand and had this objection so fast, it was obvious that they didn't even try. So that's what I'm going to say, is you have to try. Okay, you have to try to find a physical metaphor. If you can't find a physical metaphor, it's because you're still thinking too abstractly. You have to find a physical metaphor. I've never found a good abstract. Oh, look, I think that's yeah, no. I have a slide for that. Well, okay. I'll come back to this point. Moving money. So the metaphor that we talked about for double entry bookkeeping is about moving money. It's not counting money. Okay, so this is an important distinction. The physical metaphor you choose is very important, and it could mean the difference between, a successful business and a not successful business. What is a good metaphor? Good metaphors contain the answers to the questions that you're going to face. You're going to go through a design process. You're going to have to make a lot of decisions. You're going to have to face a lot of questions. Okay? The metaphor has to contain those answers. You could have different metaphors, and they're going to have different answers, right? They're both good because they both contain answers. But one might have better answers than another, okay? Just as an example, like the metaphor for Yahoo search was text search on a manually curated guide. So imagine if you had a travel guide. Here's my physical metaphor for Yahoo. A travel guide written by people with a text search, with a good index. Okay, you flip in the back, want restaurants, boom, tells you all the restaurants. What is the metaphor for Google? It's the physical linking between pages and counting the links between pages and using that to build up a ranking of stuff. Instead of relying on humans, you're relying on a large number of computers. Different metaphors, different answers, like what is a good link to show. Okay. All right, so this is something else important about collaboration is the good metaphor. Also, you should be able to discuss it. This is that teamwork that I was talking about. If we're asking questions to each other, we already have this metaphor for a common ground. We're able to talk about something. Now you might disagree, but you're disagreeing about the same thing. All right. So this is where I wanted to talk about. I've never met a good abstraction that I couldn't find a good metaphor for. I've never found one. Okay. So these people were like, "Oh, not mine." It's like, what happened is they were basically taking the idea of physical to in some odd way. Like when I mean physical, I mean like talking is physical. Passing information around is physical. They would say, well, what about quantum mechanics? It's physical. It's waves. It's particles. Like people are, you can discuss quantum mechanics in those terms. Okay. Oh, that's a good one. If you want to tweet something, here's a good one. All right, just a little list of possible physical metaphors. Some of these are really good because often what we're doing is building an information system. And we already had information systems before. When we're building software, we're building an information system. And we had information systems before we had computers. Accounting is an information system. So writing stuff down in a book is like an awesome metaphor for so much of what we do. But then so much is also different. Like queues and stuff is like conveyor belts, and there's different metaphors there. All right, so step 2. Step 1 is not is not easy, but I think it's easy to explain. Step 2, this one is a little bit harder to do and harder to explain. This is specification. You're trying to take, it's not implementation, you're trying to take this physical metaphor and like mine it, okay? Mine that physical metaphor for laws and equalities and identities, things that you can write down in a precise language. Okay, so I was always told this by my teachers: focus on the interface first, not the implementation. Okay, that's what we're doing. We're saying when you're talking about an API interface, like just the method names with the arguments, you're thinking about what are the I'm way over. You're thinking about what do the method calls mean? What do those function calls mean? Talking about the meaning of calling this thing first and then this thing and passing it this. What does it mean? It doesn't matter how it's implemented, but you have to have some meaning behind it. So that's what we're doing. We're building an interface. We're building the meaning of it. Kono-Elliott has 3 principles. We'll go into them. I'm going to express them. I like them. I'm going to express them in like software engineering terms that we're used to. Adequacy is just, can we cover every use case? Okay, that's good. Can we cover all kinds of movement of money from one account to another? Okay. Simplicity. I know that has a meaning here at Clojure conj that is very precise, but he uses it in a different way. That is kind of like a clarity and readability. You don't want it to have unnecessary bits to it. And those are the 2 important ones. I mean, they're all important. Those are the 2 ones that are ends in themselves. The precision is only there to keep the other 2 in check, because you can always make something like simpler by just like being vague and not talking about it precisely. And so precision is, can you actually write tests for this meaning? And it keeps you honest. If it's precise and it's simple, then you know that simplicity means something. Okay, so when you're going through this process, like I said, it's harder to explain than the physical metaphor. But you're going through this process and you're asking, like, what is important to preserve? Because when we've got an abstraction, we're going to be eliminating all the stuff that's not important. But you're trying to preserve stuff too. So what are we preserving? What's not important that we can just throw away? It's not going to make it into the abstraction. And then how are things related? These are like the kinds of questions, and I don't even know if this slide is that good. But you take the answers to these questions, maybe you write them down in English first, and do like a mind map or whatever, but then you start writing them down as math. So let's do this a little bit for, too long. It's already 30 minutes. Okay, what is important to preserve? Let's do this for accounting. Order of transactions don't matter. Persistence of amounts, meaning you don't lose gold, right? If you move it from one account to another, like there's always the same amount of gold. And then movement between accounts, you want to track that. You want to track where it came from and where it went to. What is not important? The color of the safe. Now, if the colors mean something, you need to keep the meaning of that color, but you don't need to keep the color, right? If it's red means it's an asset account and blue means a liability account, like, okay, but you really want to know asset, liability. It's symbolic. You want the meaning of the symbol. Where the safes are in the bank, not really relevant. There's probably some convenience about moving gold around where you want stuff in certain places, but in an information system, that's not so important. How the gold is arranged, is it in coins or bars? Yeah, that's not important. Okay, so here I'm starting to list stuff out as sentences. A book has a set of accounts, an account has a list of debits. Okay, then those things the things we already saw in math, I just put them there about debits and credits. Now here's the thing. We've got these English sentences, and we want to express them in math. And lambda calculus is math. And functional programming, Clojure, is a lambda calculus. At least a subset of Clojure is lambda calculus. So we can write our meanings down in Clojure if we keep to that subset. Okay? That's like the subset is this like very well-defined lambda calculus area of Clojure, where everything that we use has to be well-defined in the same lambda calculus way. And I'm going to use spec a little bit. I won't explain how spec works, but spec will let us talk about stuff in that abstract level. Okay, so here's the Clojure code that I'm using. This is, remember, it's meaning right now. We're not implementing. We're just giving it some meaning. So I have two types at the top. We have a book and account, but we're not defining their structure yet. So we're just saying they're not nil. Then we have a function that book accounts, which returns a list. You can see down here, a collection of accounts. Takes a book and returns a collection of accounts for that book. Now, an account has a list of debits and a list of credits. See, I can't do all this for too much. I'm going to have to cut out this whole section. Anyway, I'm going to continue though. So debit, let's just say it's an integer. It's the number of cents, okay? And then credit, integer. Now, this is debatable. I made a design decision. Could be wrong. Could be, non-optimal. But we're going to go with it, and we can always revise it later. We're still talking about meaning. We're not implementing it yet. So we have a function account debits that returns a collection of debits, and account credits returns a collection of credits given an account. Okay, so now we have this law. These two sums should be equal. Now, this is still meaning, okay? It's not implementation. But because mapcat is well defined, book accounts, we've defined it already. Account debits, we've defined it in the meaning, that is. We haven't implemented it, but we've said what it's supposed to mean. And then reduce and plus and zero, all of those things are, and equals, they're all well defined in terms of lambda calculus. So we can use them all. So what we're doing is we're constructing the meaning. The meaning of the debits for a book is the mapcat of all the account debits for the accounts in that book. Okay, what we're saying. It's like just take all the accounts, get their debits, and then put them all into one big list. Same with book credits. And then we can say, well, the sum of the book debits should be the sum of the book credits. Okay? Now, all this is to say that when you define meaning, it has to bottom out somewhere in something else that's well defined. So we bottomed out credits and debits as integers, well defined, and then we bottomed out balanced in terms of these other well defined things. It has to go somewhere. Like at some point, you're going to need to rely on something else that is well understood. Okay, so we haven't finished. There are a lot of things that were unimplemented. But Yeah, I mean, I just want to say stuff like, you're at this point where you've actually got something based on a physical metaphor that you can start to work with. It's not implemented yet, it's just the meaning, but it's like it's almost all there. Like, and you can start like eliminating stuff. Oh, we don't need this function anymore. Like, no one's using it and it's not part of the interface, so let's just get rid of it. Or this could actually be broken in two, right? So you're able to work at this meaning level instead of an implementation level. And then the other thing about that is you saw 3 of our functions were already defined. They're already implemented. They have unimplementation. And so that's one of the things about functional programming, is that because things are so well defined as expressions, as the meaning of an expression is based on the meaning of the sub-expressions, we're able to write a definition in terms of meaning and then run it, right? That's cool. Now you might have different, it's still the meaning. Like, you might not want to do an accounting system in memory, which is what we were doing. You might want it to be like in a database or something. But you have an implementation that works, okay? And that could be like a reference implementation, right? So one choice is, well, why not just use a map? Well, that's okay, but you're going to have an in-memory representation, and that could be a good prototype or whatever. But you probably want to use a database. Okay, so I'm already like at my time that I was shooting for, and that was like the first act. I'm gonna have to cut out that whole thing. That whole thing about the meaning, it was too much. All right, so here's the example. This should take about 18 minutes to explain. It's 4:57, almost 4:58. So I have until 5:15. Okay. So we're going to build a vector graphics system, and it's going to be really simple, just squares and ellipses and rotate and translate. There's a lot of other stuff, but I don't have time to develop that. So we're going to go through this process step by step. You might say, oh, I already know how to do that, or the other thing is, why not use Quill? Quill is vector graphics, why not use it? The reason I don't want to use Quill is because it doesn't obey my intuition, right? It uses affine transforms, and those are not what I want to be expressing my system in. So I had a thing about, like, if you translate and rotate, but I'm not going to talk about it. So let's go through the steps. Physical metaphor. Quill is a good implementation substrate. We'll leave that to the side. But we have this physical metaphor. What is the physical metaphor that we want to do? This is a big choice, right? You should spend some time on it. But just for the sake of speed in the presentation, the physical metaphor we're going to use, here are the different possibilities: painting, stencils, okay, shapes and construction paper. Take a piece of colored paper and a scissors, and you cut out a rectangle or you cut out an ellipse, and then you move it around, and you can rotate it and move it, and then paste it onto paper, paste it onto a board. And that's our metaphor, okay? Super simple, because we don't have a lot of time to implement something more complex. There's a lot of stuff that I'm leaving out, like you might want to scale it, and then that metaphor doesn't really work anymore. But for now, let's just pick that, and we'll work with it. So here are some things that we need to develop just to make sure that we've got the metaphor, we've got a really good idea of what we're talking about, as a team. kind of talk. Oh, overlapping. That's another thing. We want to be able to overlap. Okay. So we've got our physical metaphor, and we'll assume that we've picked one that we can use that is good, meaning we can answer questions about it. You might even want to like bust out some construction paper and scissors, and if there's a disagreement or something, you could even go back and try it, right? So that this is super clear in the team, okay? I'm going to be very pedantic about the next, when we construct the meaning, construct the meaning, we're going to mine that metaphor for all it's worth so that we can develop math that describes this system in our metaphor. So here are the questions that I said. What's important to preserve? Just quickly, there. Some of the things that, just brainstorm. I want to be able to distinguish between shapes. There's rectangles and ellipses. I want to be able to construct new shapes, meaning cut them out of paper. Preservation of shape, like moving something around doesn't change the shape. It's always going to be a rectangle. Same with the color. I choose red. It's always going to be red. Overlay order. So if I put an ellipse on top of a rectangle, like it's not going to change. They're not going to like, at some point, and when I rotate it, one of them goes on the bottom or something like that. Which, you have to think about in computer graphics. That could happen. So rotation and translation are independent. I don't want to be thinking in affine transformations where, and sorry to use a technical term, but in affine transformations, you're always rotating around the origin. So if the origin is at my elbow, you're rotating like this. I always want to be thinking about I'm going to reach onto the paper and turn it around its center. Okay, see, this is the kind of thing that the metaphor really lets you do. I can show it visually, right? For instance, rotation and translation are independent. I want to be able to move it around and turn it like this. I don't want, once I've translated it, now when I rotate it, I have to turn it like this. Okay. Rotation is additive. That means if I rotate it like this and then rotate it like that, it's the same as rotating it like that. And then same with translation. If I do this, it's the same as going like that. All right, so let's go through this. It's an iterative process, and in my slides, we actually get into some dead ends and do the wrong things and stuff. So let's go through it quickly. Remember, we're in meaning here, though we're expressing it in Clojure. So I want to be able to say what's the shape of a certain shape or a certain cutout. Okay, a paper cutout. And of course, we're not defining what cutout or shape are yet. So then I want to be able to construct some shapes. I have a rect, and it's going to take 3 arguments, color, width, and height. Ellipse takes the same, and they both return shapes, even though they are different. Now, preservation of shape. So if I move it around, it doesn't change the shape. That's what I mean. Move it, rotate it, doesn't change the shape. So we can write a spec for this that says that, well, a translate is going to take a cutout and a tx and a ty, like the vector for moving it around, and the shape of the thing I give it and the shape that the thing it returns are the same. Same with rotation. If I give it a shape, if I give it a rectangle, it's going to return a rectangle. Yeah. Now, I'm also saying, because I've got equals, that's kind of like a note I should make, the shape has to have equals well defined for it. Same with preservation of color. I'm going to add it to translate that if I move something around, the color doesn't change. And it's going to be the same for rotate, so I didn't put it on the slide. Now, overlay order. I'm going to make a function that's going to take two cutouts, and it's going to return a new cutout. All right, so this is actually, now that I think about it, it's a dead end. Right, I've said this meaning, but then what does it mean? I've already said I need a shape and a color for something. So what if I give it a red rectangle and a green ellipse? What color is that overlay of the two? Doesn't really make sense. Same with the shape. What shape is it? Doesn't make sense. So this is a dead end. Throw it away. Back to the drawing board. It's an iterative process. It's design, right? This is what you do in design. You build the prototype, it sucks, you make a new one, and it sucks, and you keep, oh, but it sucks, but it's got this cool thing. I want to keep that in the next one, It's iterative. So let's go back and scrap overlay and make this new type called a collage. So the collage is this thing that we're adding stuff to. So instead of two shapes forming an overlay, two shapes form a collage, or zero shapes form a collage. You have an empty collage, then you add something to it, then you add another thing to it, then you add, it's like a reduction, right? Okay, so that's what overlay does. It returns a collage, and it takes a collage and one overlay. Takes a collage and one cutout and returns a new collage. And a collage is not a cutout. It's different. It doesn't have a shape, doesn't have a color. Okay, so now we're going to say the overlay order is preserved. And I wrote a little property, a test check property that says, well, if you take any collage and any two cutouts, and if the cutouts aren't equal, then doing overlay A, then overlay B is different from doing overlay B, then overlay A. They're not equal. Okay. That's good. It works. Rotation, translation, independence. Really, what I mean by that is if I translate it and then rotate it, it's the same as rotating it, then translating it. So I've written another test check property for that. Rotation is additive. When I say additive, like add, that's addition, what I mean is it's commutative, right? That I can rotate, rotate it by 10 and then rotate it by 20, the same as rotating by 20 and rotating by 10. So that's what I wrote there. It's commutative. Translation is additive. Same thing. It's additive. Okay, so now it's not a dead end, but it kind of feels weird because I've actually gotten this far, and I haven't written any actual Clojure code except for the specs. So I've written all these, I've written all these tests that guarantee a certain type of behavior, but there's another way to do it. So you can write all of your specification as tests, or you could do it more constructively. So instead of ensuring from the outside that it has certain behavior, you can build the meaning constructively, meaning, well, if I need commutativity, I should just use a commutative operation, which is addition, right? So I just use addition, and it gets commutativity by itself, right? Oh, and we forgot to draw. So at some point, you're going to want to draw your shape onto the screen. So this just takes a collage or a cutout, right? Takes a collage or a cutout. Okay, so we've gone through one iteration, or kind of two iterations, really, and that's how design works. But I don't like how we've just defined everything as in terms of tests. All the meaning is in terms of tests. That's fine. It's just it doesn't feel right. So let's go back. Start over. we only need two types. We need cutout and we need color. Okay, so cutouts don't have a shape anymore. We've gotten rid of that type. Color, we're bottoming out RGB. It's not an interesting problem. We're just not going to talk about it. It's a choice, right? And I'm making that choice here in this iteration. We're going to define the same meanings, but we're going to do it constructively. So here's the other thing. We're defining, I didn't mention this, but cutout is now a function. You see, I use fspec. That means that it's a function. The type is a function. And so two things. We can use a function, always use a function for anything. That is a property of lambda calculus that we can exploit. And that's one of the cool things about lambda calculus. That's why I use functions for things when I'm developing meaning. Doesn't mean my implementation is always functions, because they're not always the most efficient way of representing stuff. But you can't go wrong by starting with a function when you're defining meaning. You can always refactor it out later. Okay, so that's a function. Also, functions have this property, like a pure function, has a property that you can specify the things that are variable, those are the arguments, and you can specify the relationship between the arguments and the return value. So you are using this property. Remember we said that shape and color shouldn't change. Well, if we just make shape and color closed up in that function, and the only things that we're changing are the translation and the rotation, then we're constructing that meaning using other parts. Okay? So we're exploiting the already built-in meanings of lambda functions to build our meaning. Okay? So what does rect look like in this case? Another thing we can do, okay, is we can kind of say, look, Quill is a well-defined system. We're going to be implementing it in terms of something like Quill. So Quill is a well-defined system. That's where we're going to bottom out. Okay, we can make that design decision. We're not implementing it yet. We're just saying that when we talk about rotation, these are the affine transformations, which are well-defined, that we're going to go through to rotate and translate and whatever. Okay, so this is what it looks like. Rect takes a color, width, and height and returns a function that takes the tx, ty, and the r, the rotation. And it does some affine transformations in the right order, because that matters. It chooses a fill color, and it draws a rect, and it does a pop. Okay, so those are affine transformations and choosing the color, and what it draws is closed up in there. Okay. I kind of want to get rid of this these specs down here. All right, ellipse is the same, except we've changed it to draw ellipse. It's okay that we have these specs in there, it's just redundant. Okay, meaning. This is meaning again, but we're doing stuff in terms of other stuff we've defined. So when we translate a cutout, we're actually going to return a new cutout. That's a function. And we're showing that, yes, translation is additive because we're using addition, right? We're constructing that meaning. So we have tx and we have ty, and the r is just getting passed through. All right, rotate. Same thing. Rotation has to be additive, so we're going to use plus. Now overlay or a cutout does not have a color and shape anymore as a property that we can read, right? So that we can now ignore that, and we can make an overlay that's a cutout of the two. I mean, it's a combination of the two. And we're using the property of quill that says when you draw something after something, that second thing gets put on top. So we're saying B is going to be on top. You know, like if a green square is drawn on top of a red square, the green square is going to show when they overlap. And then draw just calls the function, but with zeros as the origin. You give it the origin. That's cool. And so now we can see if it works. Another cool thing about functional programming, I mean, I'm sure you could do it with object-oriented programming too, so I'm not going to say this. I shouldn't say that. But the cool thing about working on meaning in terms of well-defined stuff is that you can run your meaning, runnable meaning. So we're going to run it. It might not be the most efficient implementation, but we can see if it does what we want. So let's set our draw up, and we're going to create a red rectangle and rotate it by 0.2 radians, then translate it at 100, 100, and we're going to draw a green ellipse at, that's the size, 150, and then translate it 200, 100. Then we're going to draw the overlay of R and E, and we see that E does show up on top. That's good. That's what we want. And then we're going to change it just by 1 bit. We're going to make that overlay, and then we're going to rotate it by 0.5. So we're rotating the entire overlay. And we see what happens is we thought it would just rotate together, but they don't. They separate out when they rotate. So something's wrong. Like we're rotating around something besides the origin. And if we go and look at our code, we see that what we're doing is we're rotating the two cutouts independently. We're passing in that R that rotates the two independently. What we really want, we have to revisit our metaphor. What we really want is if we got two things together, overlaid together, I mean, they don't have to be on top of each other, but we're treating them as a group. What we really want is that we're going to put our hand on them. Okay, here's the physical metaphor part. We're putting our hand on it and we're rotating them together. Like their relative positions should be the same when we rotate them. So how do we do that? Because I could put my hand here, I could put my hand here and rotate them. You know, there's different ways to grab those things. So we kind of have to say where we're going to grab them. Okay, where's that center? Like the center would be my wrist, right? Because I'm rotating around my wrist. Like where is the center of what we're grabbing? See? You need to do the physical metaphor. You can't do this process without it. Okay, so now when we overlay, we have to say the center. Okay, we have to say where we're going to be grabbing them. And it's kind of boring, but the affine transformation that we have to do, we have to like move them back to the center. I mean, move the center back to the origin so that we can rotate around and then move it back down to where it was before. So that's what those two extra translates are, and that's why we're negating the center. So now when we do this, we see that we are able to rotate them together without them changing relative positions, which that's what we wanted. Okay, so it's kind of weird to talk about implementation now, right? Because we saw it running, like literally we saw the video of them rotating. I'm just rotating it over time. That's why that system current time millis is there. So I'm talking about implementation, but we have a runnable meaning, but it's not an implementation. Like, we could do it differently. What did we lose in this implementation? Because we did lose quite a bit. And specifically, I'm talking about choosing to use functions to represent cutouts. Because once we do that, you can't inspect it. It's a black box. What shape do I have? I don't know. You can't do a quality comparison on functions. I mean, you can, but you'll get the wrong answer. And it's not testable. The only way you could test this is to like actually render it to something like a value. Like, you could render it to a buffer and then compare the two buffers, and you don't really want to be doing that. And then you can't serialize it. It's a function. You can't write it to a disk or to a database. So I'm not going to go over implementation, but you can use refactoring and whatever to take it from a function, refactor it into data structures that you could then interpret. Which is a really cool refactoring, by the way. That's another talk. Okay, I did pretty good on that section. Only 4 minutes off. This is Isaac Newton. He was a master abstraction builder. The reason I put him on here is because he built several important abstractions that we use still, including optics and what's called Newtonian mechanics. Newtonian mechanics, in order to make it a mathematical model, he had to invent calculus. Okay? He had to invent calculus to do that. So he has a huge book that's trying to explain mechanics. Basically, how do things move and interact with each other in the physical world? Not just on Earth, but also in space. Because that was a huge problem at his time. People thinking that things on Earth acted differently from things in space. But he had to build so much of his infrastructure in order to even express his model, his abstraction. He had this quote: "If I have seen further, it is by standing on the shoulders of giants." It's often used to say that, look how humble he was. He was actually using it to make fun of a short guy who was his rival. So he was like, I wasn't standing on that guy's shoulders, it was giants. So he wasn't a very humble man. But there's a third interpretation, which I prefer, which is that this is a method. He's actually telling you how to be like him and invent stuff like he did. You have to stand on the shoulders of giants. You have to read books. You have to see what's been done in your field before. You have to rely on the work that was done before. And the thing about the difference between us and him is, back then, they were just putting this stuff together. There wasn't a lot out there. And literally Isaac Newton could read all the books, all the good ones that were out there, and also waste a lot of time on stuff like astrology and numerology. So there's a physical manifestation, physical metaphor for his quote there. But when you look at it, if you plot it over time, the giants have been getting bigger. The shoulder height, at least, is bigger because over time we're able to aggregate more information, use each other's models. We have Newton's calculus in there. Also mechanics is in there. So when we build a new abstraction, we can define it in terms of those things. So it's an exponential curve. The giant shoulder height is growing exponentially. My teacher told me I should always label my graphs, so there we go. What I'm trying to get at is that at some point this exponential curve is going to be so steep that we're going to be creating new abstractions, useful abstractions, like all the time, every day. And I'm contending that we've already passed that point. Not only do we have access to all of these abstractions on the internet that we can just read about, right? And you know, people have documented them in nice ways already, way better than anything that existed at his time. We have computers. We can build the abstraction and run it. We can see it work. We can see if it works, and we can modify it. We can revisit the metaphor and like re-implement the thing in minutes. We can do this all the time. I mean, if Newton wanted to calculate the like orbits of the planets, like it would take weeks to do all the calculations. And so he had to get the model right faster. We can mess up so many times and still have a good abstraction by the end of the day. So my contention is that we as programmers have this huge power to make the world better, to build abstractions that are meaningful, that are useful, that can bring tremendous business value. And we can do it so quickly, so easily. Thank you.